Hey y'all, welcome back to another round of physics. And as promised, I said this time we should probably look at how magnetic fields interact with current carrying wires. Off the cuff again, let's say for a moment I have my x axis and my y axis. So we'll call x again this way, we'll call y this way, and we'll take z out of the board. Z. And yeah, let's go at it. Let's say that our bar, our wire, has a length of L, just say L, and so there's our length of L, and we'll say that it's at 30 degrees in the XY plane. And furthermore, we'll just make our lives more difficult. Let's say that the magnetic field is in the, I don't know, 135 direction, Tesla. Go ahead, get an expression for the magnetic force acting on the wire. Oh, and say that the wire is carrying a current I. We'll just say it's a current I again. Got it? Good. Sweet. Well, first of all, we should probably get an idea about the direction of dl. Right? What direction is dl? Well, yeah, this is a little bit more tricky now, right? Our dl is in this direction. We know that, okay, well, when I take a step, I'll zoom in there. If I take a step dl, how far have I gone in the x direction and how far have I gone in the y direction? Keep it in mind, this is 30 degrees. Good, 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 good. Well, I've gone a step dl, cosine, good, in the x direction. We'll say cosine of 30 degrees. That's the x direction. We've gone a step of dl, sine of 30 degrees, and 0. Right? Okay, good, good, good. So I'll say dl, cosine of 30. Oh, maybe I should ask. 30, 60, 90. Cosine of 30 degrees is, good, root 3 over 2. So I'll just put those in. Sine is 1/2 and 0. Good, good, good. So now we're in a position. Let's go ahead. Let's break it down. We have an expression for dl. Let's go ahead and calculate what dl cross b is. You got it? Sorry, I'm going to set up my usual. So this is root 3 over 2. This is 1/2. This is 0. And here we said 1, 3, and 5. And I guess I multiply those by dl, so I'll just put that out. Okay, so this cross product, let's go through it. Again, it would be x hat times 1/2 times 5 dl. And then I have, oh man, we have y hat times 0 times 1. Then we have z hat times root 3 over 2 times 3. But wait, there's more, right? We still have to do the negative one. So I have negative, let's see, 3x hat and 3 times 0 dl. Oh, good gravy. I forgot the dl's in here. And then minus 5 3/2, so y hat. We have root 3 over 2. And then we have minus 1 times 1/2. Again, I forgot that dl. Z hat dl. Well, at least we can get rid of a couple of these. right? That 0 helps us out. We don't have that component. We don't have that component. Okay. And I'll go ahead and use this white space up here. So at the end of the day, what do we have? We have that our force of our magnetic field is equal to the integral of the current times dl. So we have a dl in all of these terms, so I'll just pull that out. And then we have something that says the x hat direction is 5/2 minus, let's see where we have it. Oh, that's it. Right? Excuse me, I'll go ahead and write the x component here cancels, so or goes away. So what we have is 5/2 x hat. How about the y hat? Well, that's right here. Minus, we'll say 5√3 over 2 y hat. Okay. And then we have, okay, z hat has a little bit more to it. Z hat times, we have 3√3 over 2 minus 1/2. There is our cross product between the magnetic field and the direction of the current. And of course, I should say, what's our limits of integration again? I'll say 0 to L. We're home free. The upshot, here we go. Here's an upshot here. Because we've done this cross product, notice x hat, y hat, and z hat, those are all constants. Yes, they're vectors, but they're constants. Which means when I do the integration, those constants can get pulled out of the integral. You notice dl, I is a constant, and we just have to take care of this dl. Well, shoot, the integral of dl is just L, and evaluated at 0 to L gives us big L. So at the end of the day, we have I, L, times this vector stuff. In fact, I'll just put it into component notation now. 5/2 negative 5√3 over 2, comma, what is this? 3√3 minus 1 over 2. And there's the direction of the force. Boom, done. Pretty neat, huh? Now, part of the reason this integral was so easy was because of how we decided to express the direction of the current. Okay. I just said, okay, dl. Really what you're doing here when we did this integration is rather than integrating along the x direction and the y direction, you integrated along the wire itself. Now notice you didn't have to do it this way. The reason that it was so easy is because I expressed dl the way that we did. Okay. Let's say we wanted to do it a different way. That's fine. Let's say that vector dl is equal to dx, comma, dy, and 0, since it's confined to the xy plane. That means that when you do this dl cross b, what do we end up with there? X hat, y hat, z hat. You end up with dx, dy, and 0. And I guess we call this 1, 3, and 5. So what do we get out of that? Okay, well, we get x hat 5 dy plus y hat times 0, so we don't need to worry about that one, plus z hat dx, and that's times 3. And then we have minus. So we have 3, 0, x hat, so we have x hat times 0. We have minus 5 dx y hat. And then we have minus dy z hat. So at the end of the day, what do we have? We have the x component is 5 dy, and I'll go into triplet notation. Then the y component, the x component, that's 0, this is 0. So the y component is 5 dx with a negative sign. And the z component is 3 dx minus dy. Yes, be careful. Okay? The x component of the vector can have integrals in the other two components. So what does this mean? This means, okay, our force due to the magnetic field can be written as the integral from I, say dl cross b. But now we've broken it up. We're going to break it up into 3 different integrals. We say, okay, well, I want to do the x integral. So I have the x component. This would be I, and the x component is 5 dy. And I should ask, okay, sit and ask yourself for a second, what are the limits of integration for a y integral? Good, good, good. 0, that's the start. And I go to L sine of 30 degrees. Right? I don't go from 0 to L. I go to L sine of 30 degrees. So this first integral gives us something like L times sine of 30 degrees times 5i. Well, sine of 30 is just 1/2. So I get 5/2 I times L. How about the y component? FB in the y direction. What do I get there? Well, I say I have an integral of I, and the y component is given by -5 dx. What's the limits of integration for x? Good. Cosine of 30 degrees. And so I and -5 are constants, and so I end up with something like L cosine of 30 degrees times -5i. And of course, our 30-60 triangle, 30-60-90, cosine is √3/2. So I have -5 √3/2 times IL. But wait, there's more. Let's do the last one. FB of z. And this one, of course, is a little trickier, right? I have the integral of I, and I have 3 dx minus dy. Well, I have to break that up, right? My integrations are with respect to different things. This is the integral from 0 to L cosine of 30 of 3i dx minus the integral from 0 to L sine of 30 I dy. Go ahead, you got it. Right, what does this give me? This gives me 3 √3/2 IL minus 1/2 IL. And notice the 3 pieces that we have, I'm circling them in purple. These 3 should match what we had in the previous problem. 5/2 IL, -5 √3/2 IL, 3 √3 minus 1/2. So it works out either way. If you would prefer like I said, if I express DL this way, I have I think the technical term is parameterized. I've parameterized the length of wire according to DL. Here, you're just integrating, you say dx and dy, and you use the limits of integration to actually integrate along the proper DL. Either way, you get the same thing. Pretty cool, huh? Good. So the last thing I thought maybe we should think about is this. Let's say I have a loop of wire. We'll call it a square loop. Yeah, we'll call it a square loop just for kicks. And why don't we say that it has a length of L? Okay. So think of this as the side view. Okay. And let's say that we run current, I don't know, we'll run it counterclockwise around the loop. So the left side, it's into the page. The right side, it's up the page. In fact, I'm going to do an overhead view as well. So if I'm looking top down on this wire, I see on the left side, it's going into the page. And on the right side, it's coming out of the page. And the current on the top branch is running towards, there we go, the into the page side. Good so far? Now the next point, let's go ahead and I'm going to say that this wire, this loop of wire, is free to rotate about a pivot point. Say the center. So in the overhead view, I'm going to mark that pivot point with an X. Okay. And the last piece to the setup is this. Let us say for a moment that again, we have a magnetic field and we'll put it out of the board. Here's the question I have for you. Okay. If it's carrying current I, it's a square loop, a length L. The question I have for you is, what is the torque acting on the loop? Go ahead, take a couple minutes, see if you can start your way through that. Got it? Sweet, good. Okay, so let's go at it. First of all, we should probably ask ourselves, what's the definition of torque? What do we define torque as? And it is defined as R cross F. Let's keep in mind for a moment that R is the distance to pivot, the pivot. Okay. And F is where the force, or the distance to the pivot from, okay, I'm sorry, I should say distance from pivot to point of application of the force. Okay. Let's keep that in mind. Now, what's the force? What's responsible for the force in this situation? The magnetic field. Okay. So this would be the force of the magnetic field acting on the wire. Now notice how many different DLs, if you will, do I have for this square loop of wire? 4. So when I want to calculate the net torque acting on this wire, I really need to do a summation over those 4 pieces. Those 4 pieces, call it B. They're going to have different forces acting on them, and so we should sum up over the 4. So let's go ahead. Let's think about, first of all, let's get an idea about the force acting on each of these 4 pieces of wire. So the top wire, we say, okay, current's going to the left, magnetic field's out, it will experience a force going up. How about the side one? Well, it's going down, the magnetic field's out, it will feel a force pulling it to the right, the left, excuse me, the left. Yes, okay, gotcha. Right? Bottom one. And the top one. You probably already got all these. Good, good, good. So what's the torque that this is going to experience? What's the torque, the net torque, that this loop will experience? 0. Good, good, good. Well, why is it 0? Let's get an idea here. Well, for this top segment, okay, this is the side view, by the way. Excuse me, I should have put this. This is side view. For this top piece, okay, what's the distance between the location of the pivot and the location where the force is being applied? I'll do the forces in green here. I'll label that top. It's 0, right? The force is being applied at the pivot location. It's 0. That's not going to do anything. Good. How about this? How about we'll take the right side for a moment. F right. I'll call it FR. How about that one? Also 0. You can see that from this overhead view. FR would be this way. In fact, I'll put FL here too. FL. What can you tell me about the direction of the R vector pointing from the pivot to the point of application for the right-hand segment? The direction of that is parallel to the direction of the force. So if this guy is parallel to this, the torque is 0, equals 0. How about the left-hand side? Also 0. How about the bottom? Also 0. They're all 0. Okay. Yeah. Good. So let's take the same idea, except I'm going to change it just a little bit. Let's now say that rather, and I'll just do the we'll still have the loop of wire. We'll still have the current running counterclockwise. Okay. We'll still have the magnetic field out of the board. Okay. Now the difference is here is and it's hard to draw from the overhead view, so we'll still have that pivot point. Now what I'm going to do, oh, excuse me, I don't know what I did there. What I'm going to do here is I am going to set, let's say that the wire, the loop of wire, is not quite oriented with the magnetic field. In other words, here's my pivot point right there, and my magnetic field, which I'll do in, I guess I'll do it in green here. My magnetic field is going this way, B. Now, let's get an idea. Go ahead. Is the torque on the loop going to be 0? No. Good. You probably already see that, right? Like, let's take this inside one, this one that's going into the board. You can see if it's going into the board, hands go into the board. That's the direction of the current, I. B, palm is facing down. That means the force is going to be off to the left. In other words, you're going to get a force this way, FL. Well, how about the right-hand one? Well, current's coming out, the magnetic field is still down, and you're going to get a force going to the right. And what are those two forces going to want to do to the loop? Cause it to rotate. Very good. You see it's going to pull. It's kind of like pulling, and that will cause the loop to rotate. As seen from above, it'll cause a rotation in the counterclockwise direction. So notice the difference. Previously, I should have drawn that in. The magnetic field, for this case, the magnetic field is going this way, B. In this case, because the loop is angled a little bit, there's going to be a net torque. And I should highlight that net torque is acting in order to get the face of the loop to be parallel to the magnetic field. In other words, if I will, the n hat of the loop is parallel to B. That's what the torque is going to want it to do. Notice here it's already, n hat is already parallel to B. Just as an exercise, maybe I should have put this in just to be a little more clear. If I put x to the right and y being up and z being out, that's the side view, then the overhead view will be x to the right still, z is going down, and y is actually the one that's coming out of the board at you. Okay. Just to kind of orient your mind there. Well, let's get an idea. Let's get an idea about what the torque is acting on, let's say, that left-hand piece. So this piece of the wire. Well, you have R cross F, L. Okay, what's the magnitude of that vector? Let's start there. Yeah, the magnitude of that vector, we'll say R. The magnitude of that vector is just simply L over 2. Let's get a magnitude for this guy. Okay. Good. Okay. Yeah, let's see. The magnitude of this guy, force L, will simply be, well, we have I dl cross B. But for this case, dl is in the negative y direction downwards. B is in the negative z direction. All right? So we get something that says I, L, B in the negative x direction. Right? We already did that with the cross L, Z, or in the negative y, positive z, we get the negative x direction. And it's a distance of L, right? And magnitude. So there we go. We have this one, and we have, oh, excuse me, magnitude. Should have put magnitude in. So this would be F of L equals ILB. So we're almost home free. We have that the magnitude of the torque acting on that left wire, the one where the current's going into the page, I'll write this as the magnitude of R, the magnitude of FL, and we'll put sine of the angle between the R vector and the F vector. So we don't know what that one is. That depends on the initial orientation of the loop. So we had something like this. And so theta will be the angle between the two. Okay. So we don't know what that is. That's just a problem setup. I guess the other way we say it is you have the angle theta right here. So at the end of the day, though, let's go ahead and look at this. The magnitude of the torque on the left-hand side is simply equal to L over 2 times ILB times sine of theta, where again, this depends on the angle. what was the initial angle that the loop was set up at. Or if I prefer, I have something that says I L squared B sine of theta over 2. But wait, there's more. Let me ask you this. Go ahead, take a minute, see if you can work through it. What's the magnitude of the torque acting on the right piece of wire? Go ahead. Good. You probably already see it. It is the exact same as the magnitude acting on the left piece. Convince yourself, right? R, the distance from the pivot point to the point of application of the force on the right-hand side is still L over 2. The magnitude of the force on that right-hand wire is still ILB. You'll notice that instead of being in the negative x-hat direction, it's now in the positive x-hat direction. And you'll notice as well that the angle between R and, we'll say FR, that angle is still theta. And so at the end of the day, the magnitude of the torque acting on that right-hand side is simply given by IL squared B sine of theta over 2. What would that say about the net torque? Oh, and incidentally, keep in mind, we can use our right-hand rule again to get an idea about the direction of this. Go ahead, do it. Right? If I have R going that way, that's my fingers. F going to the left, the negative x direction. This gives me a torque in the positive y hat. How about this one? The right-hand side. Well, I have R going that way. I have F going this way. That means my torque is still out of the page, still in the y hat direction. So now I'm in a situation where I can say where the net torque is. It is the torque on the left-hand piece plus the torque on the right-hand piece. And that is simply IL squared B sine of theta over 2 in the y hat direction. And I have 2 of those, so 2. Oh, goody, goody. I get a cancellation of those 2's, and I get that the net torque is the current being carried in the loop of wire times L squared B sine of theta in the y hat direction. Pretty cool, huh? We can go even more general. Okay? As it turns out, if you notice, if I think about what happened here, this L squared, okay, one of those L squareds came from R, the distance from the pivot point to the point of application of the force, and another one came from the length of the current carrying wire. In other words, integrating DL. And maybe I should say this one came from having L over 2, and then I had 2 wires to complete the loop. In more general, if I had used a rectangular loop and said, okay, well, let's call this distance B and this distance A, you would have noticed that instead of getting an L squared, I would have gotten something like B times A sine of theta in the y hat direction. Or even more generally, and this is a heuristic argument, I'm not going to go through the proof. More generally, what you'll end up with is not B times A or L squared. You'll end up with the area of the loop. So a more general expression would be something like I times the area of the loop, excuse me, I dropped the B, times the magnetic field times the sine of the angle between the two. Okay? And I could go even further than this. Okay? You go even further. Okay? Generally, this is for more your information. Generally, this IA is sometimes called the, I think it's the magnetic moment. Of the loop. Excuse me, loop. Generally, it's given m in a vector. Okay. Now, that's a definition. We are going to define the magnetic moment of the loop, which we call m. Little m is defined as the current in the loop times the area of the loop. And because I want to make it a vector, I'll call it n hat. And what I mean by that is if I take the area of the loop, I'll say n hat is that unit vector perpendicular to the surface. Okay. Good so far? So more often than not, as we advance, you'll see that the torque, the net torque on a current carrying loop is given by M cross B as in boy. Okay. Again, that's just a little extra for you. From the overhead view, so again, the overhead view, here's my loop. N hat would point this way, N hat. Okay. B is pointing this way, B as in boy is pointing that way. Okay. And if we remember, we called this theta. Well, if this is theta, this angle, that is also this angle. So this angle is theta. But N hat is perpendicular, which means this is pi over 2 minus theta. And let's see, N hat is perpendicular, but B is perpendicular to the dashed line right here, which means this angle has to be theta again. So that's how I managed to lump that sine of theta back in. It's actually, that's how I've reintroduced it as the cross product. So there's the net torque on a current carrying loop. And notice, okay, you could rationalize your way through it here. Notice that that loop tends to want to align itself so that N is parallel to B. When you have a current carrying loop in a magnetic field, it is going to want to align itself so that that N hat is parallel to B. This is also, we'll latch back onto this in a while. Okay, this is how we get objects magnetized as well. Well, that's all I have for this discussion. Those are just some prompts for future thought. I guess thank you for your attention. I'll see you next time.